Hello everyone! First of all, thank you very much to the organizers for putting up together this meeting and for giving me the opportunity to present this work that I have been carrying on with my collaborators on discriminating between different scenarios for the formation and evolution of massive black holes with LISA. So as you probably know, massive black hole binaries are one of the main targets of the LISA mission. And by observing several of these systems, we'll be able to infer the population of massive black hole binaries in the universe. And because this is the end product of a long evolutionary path, these observations will inform us on how massive black holes form and evolve across cosmic history. Moreover, the evolution of massive black holes has been found to be strongly correlated with the one of the host galaxies. So these observations will inform us more broadly on the astrophysics at play in galaxies. So for this population of massive black holes, we use a model that was proposed a few years ago. So there, massive black holes can form as light seeds from remnants of pop-3 stars, or as heavy seeds from the collapse of protogalactic disks, and these two scenarios are considered separately. However, it is unlikely that the universe could be described by one single model, so to account for that, we introduce a mixing fraction between the light seed and the heavy seed model, and we treat it as a hyperparameter controlling the population of massive black hole binaries. So to give you an example, here I'm showing the distribution of parameters predicted by the model for different values of the mixing fraction. So in green you have the pure heavy seed case, in blue the pure light seed case, and in orange for a given value of the mixing fraction. So as you can see, the chirp mass distributions look very different, and we expected that it should help us constrain the value of the mixing fraction. Also, maybe the redshift distribution, as you can see. However, now if we impose a signal-to-noise ratio threshold of 10 and plot only the detectable events, you see that the chirp mass distribution still look very different, but not the redshift one anymore. On the other hand, now the distribution of effective spins looks much more different between models, so we expect that it should help us constrain also the value of the mixing fraction. So our goal here is to infer the posterior distribution of alpha given an observed dataset. And for that we use the hierarchical Bayesian framework, so which gives this formula for the posterior distribution. So you have three terms there. The geometric one here, so that term here is the probability distribution function of our theoretical model. So this geometric term is is comparing between the observed dataset and the predictions of our model. The selection term here, which accounts for the fact that not all the events are detectable, and the Poisson term, which account for the rates. But we'll be marginalizing over the rates, so we drop that term. So what we do is that we generate data sets from our fiducial model that I presented earlier, and use the same model in our data analysis pipeline, so in this hierarchical Bayesian framework. So here I've generated a data set with an increasing number of observed events, and you can see that the distributions tend to peak near the injected value, and they become narrower as we increase the number of events, as expected. To get a more global view, here I've generated several data sets with different values of the mixing fraction, so given here by the color scheme. So these data sets contain an increasing number of events, and here on the x-axis I'm plotting the error on alpha, and on the y-axis the bias, which we define as the maximum posterior point minus the injection point. So as you can see, both tend to decrease as you increase the number of events, again as expected. Note also that the fact that the points are roughly equally distributed on both sides of the horizontal axis shows that we have no systematic bias in our analysis. So let's look now at physical prediction, so we can compute the posterior predictive distribution. So this is what do we predict the population distribution to be given an observed data set. So here on the left panel I'm showing one of the worst cases that you get. So you can see that there are some discrepancies but still you have a reasonable agreement between what we infer the population to be and what it really is. On the on the right panel, here I'm showing one average case, which is in fact what we get most of, the level of agreement that we get most of the time, which you can see is in fact very good. However, there was an important assumption so far, that was we use the same model for generating the data sets and in the Bayesian pipeline. So now we want to test if this model is robust, if the observations are different from our theoretical model, which is most likely the case, in fact. So we use this more recent model, and so they use the same seeding mechanism that our fiducial model, but they also consider the effect of supernova feedback, which could quench the growth of massive black holes, and additional delays between the moment where dark matter halos merge and when massive black hole binaries merge. So this is just to show you now how the distributions look like. So you can see that the chirp mass distribution looks more or less similar, but not the other ones. In particular, redshift and spins distribution look pretty different. So we expect that this could be a problem for our pipeline. And this is indeed the case. So here I generate a data set which corresponds to the pure heavy supernova delay model, and I use the fiducial model in the Bayesian pipeline. So you can see that, for instance, we can reasonably well reconstruct the distribution of observed events for the chirp mass. So on the left panel, we're showing the distribution for events that are above the threshold. But on the right panel now, we're showing the intrinsic population without any signal-to-noise ratio threshold. And you can see that even for the chirp mass, the agreement is not very good, and even worse for the other parameters, in particular redshift and spins. So to conclude, before concluding, I would like to stress an important technical point. So to use this pipeline, you need to be able to estimate the probability distribution function here, and the selection function, which is the fraction of detectable events as a function of the mixing fraction. However, since we're not using an analytic model for the population distribution, we need to evaluate these terms from simulation points. And we need enough points, otherwise these estimates will not be very accurate, and you could get a systematic bias in the analysis. So here, what we have done to evade that is that we build a kernel density estimation to estimate the probability distribution function, and we treat that as being the true population. So this can be seen as a limit where we would have many points to build a very accurate estimate of the probability distribution function. And also because in fact the result that we get with this kernel density estimation is not very different from the population distribution we get from numerical simulations. They're very similar. So we do not expect that all the results we have presented so far should change significantly without this assumption. But just to show you what I was telling you concerning the bias, so here I'm showing the bias versus error plot again, but I've used here to compute it a selection function that I computed with less points, with fewer points. And you can see that it is less accurate, and then it leads to a systematic bias, as you can see by the fact that there are more points below the horizontal line. So to conclude in this work, we have introduced a mixing scheme between pure models, and we have shown that with the pipeline that we propose, it allows us to infer correctly the population of massive black hole binaries in the universe, as long as the observed data sets are similar enough to our theoretical predictions. But since this is will most likely not be the case, we are currently working on a model agnostic approach where the population of massive black holes would be controlled by physically meaningful hyperparameters such as the initial mass distribution or the time delay between dark matter halos merger and massive black hole binaries mergers. So this is a work currently ongoing. And finally, I've also stressed an important point here, the fact that for this kind of analysis so based on simulations to work, many points from numerical simulation will be needed, otherwise we'll get systematic biases. And we can estimate that we need at least a few tens of thousands of points to do that. So thank you very much for your attention, and I will be very glad to take any of your questions.